Greetings, welcome to this new video about Thevenin's theorem. In this video I will demonstrate the application of Thevenin's theorem through a step-by-step example explanation. By following along carefully, we'll gain a clear understanding of how to apply Thevenin's theorem to solve practical problems. Let's dive in and begin with solve the problem number 3. Let's consider this network consisting of 4 resistors labeled R1 through R4 as well as 2 independent sources, Vs and Is. The question now is to find the Thevenin's equivalent with respect to terminals A and B. Let's move on to the solution. By applying the Thevenin theorem between terminals A and B, we can replace this circuit with a voltage source in series with a resistor, which will be denoted as VTH and RTH. I will start first with the determination of the Thevenin's resistance. This step can be done by removing all independent sources in the circuit, which means the voltage sources will be replaced by a short circuit and the current sources will be replaced by an open circuit. The Thevenin resistance represents the equivalent resistance between terminals A and B. That means RTH is equal to the series combination of R1 and R2 in parallel to R3 connected in series with R4. Therefore, RTH can be calculated using the following formula. And if we replace the resistors with their numerical values, we obtain RTH is equal to 20 ohms. After finishing the determination of the Thevenin resistance, we proceed to calculate the Thevenin voltage. The Thevenin voltage is basically the open circuit voltage calculated between terminals A and B. To find the open circuit voltage VOC, I will apply the nodal analysis method. But first I will consider I1 is the current through the resistor R1, I2 is the current through the resistor R2, I3 is the current through the resistor R3, and I4 is the current through the resistor R4. By applying now Kirchhoff's current law at node 1, we can write I1 plus I2 minus Is is equal to 0. And according to Ohm's law, I1 is equal to V1 minus Vs over R1 and I2 is equal to V1 minus V2 over R2. And if we replace the resistors and the voltage with their numerical values and we continue simplifying this equation, we obtain 2 times V1 minus V2 minus 80 is equal to 0. Now by applying Kirchhoff's current law at node 2, we can write I2 minus I3 minus I4 is equal to 0. And according to Ohm's law, I2 is equal to V1 minus V2 over R2 and I3 is V2 over R3 and I4 is V2 minus V3 over R4. And if we replace the resistors with their numerical values and we continue simplifying this equation, we obtain 1.6 times V1 minus 5.8 times V2 plus V3 is equal to 0. Let's move on now to node 3. By applying Kirchhoff's current law at node 3, we can write I4 minus Is is equal to 0. The current here is 0 because we have an open circuit. And if we replace I4 by V2 minus V3 over 16 and we continue simplifying this equation, we obtain V2 minus V3 minus 80 is equal to 0. Now from equation 1, we can write V1 in terms of V2. That means V1 is equal to 0.5 times V2 plus 40. And from equation 3, we can write V3 in terms of V2. That means V3 is equal to V2 minus 80. And now by substituting A and B in 2, we derive one equation in terms of V2. And if we continue simplifying this equation, we obtain negative 4 V2 minus 16 is equal to 0. That means V2 is equal to negative 16 over 4 is equal to negative 4 volt. And from equation B, we have V3 is equal to V2 minus 18. If we replace V2 with its numerical value, we obtain V3 is equal to negative 84 volt. And if we look here, VOC is equal to V3 is equal to negative 84 volt. That means VTH is equal to negative 84 volt. From here, the equivalent Thevenin circuit with respect to terminals A and B can be replaced with a negative 84 voltage source in series with the 20 ohms resistor. After completing the calculations, I perform a simulation using SPICE to verify our results. Now let's proceed to the SPICE environment. Our network consisting of resistors R1, R2, R3, and R4, an independent current source IS, and an independent voltage source VS, has been drawn in SPICE simulator. Next, I will connect a load to both the original circuit and the equivalent Thevenin circuit and simulate their behaviors. Let's move on to analysis. This analysis calculate nodal voltage. We can see here that the voltage across the resistor RL or across the load is equal to negative 4 volt in the original circuit and is equal to negative 4 volt in the Thevenin's equivalent circuit. Upon simulation, we can observe that the two circuits have identical behavior when we connect a load between terminals A and B. This outcome confirms the accuracy of our calculation. Alright, thank you for watching this video. If you have any question, do not hesitate to contact me by email or leave a comment under this video and I will answer you as soon as possible. If you like this video, don't forget to subscribe and share. See you next time in another example about Thevenin's theorem. Take care and bye-bye.